Hi, welcome to a brand new unit on compression. Till now, we have been looking at the entropic compression problem where we are given symbols from a sequence. We are given symbols x1 to xn, and we either know the model, the distribution which generated them. Mostly, we looked at independent distributions, or we don't. We looked at the universal case as well. But we would like to compete with the best scheme that knows the distribution. And we saw that that best scheme can attain average length very close to n times entropy of p, the individual distribution, and we can even compete with that. Now, in this unit, we will look at a very different kind of compression problem, which is also practically very relevant. And here we'll talk about the compression of databases. So I've kept the title a bit grand, but we look at a very specific problem because I just want to give a flavor of these problems. The important point in these problems is that instead of using entropic compression scheme, we use hash-based compression schemes. And we have already encountered random hash in the beginning of the course, and now we'll again use random hash and its efficient versions to enable compression of databases. So the problem that we are looking at is the following. So this is just one specific problem. So we are given entries x1 to xn. These n entries are there from the same alphabet, let's say, from x. So n entries from this x. Question is, how do we store them in a database or store them efficiently, let's say. To answer queries about x1 to xn. Okay. So how do we store them efficiently? So that's basically a compression problem, except that we have added efficiency part here. So answer queries, and this answering the query part. So this efficiently here refers to small storage memory, small memory needed. And this answer, this part also, we want to do it efficiently, computationally efficiently. Okay, that's the goal. So how do we do this? So in particular, we are looking at one specific kind of query, search query. So in this query, what we will see is that you're given a y from x, and you need to check if y belongs to these entries x1 to xn or not, which you have stored. So y lies in, I'm citing here, so maybe I'll write it as y belongs to x1, x2 or not. So the answer to this query is yes or no. So just a binary answer. Okay. So the question is, if you want to answer these queries, how do you store x1 to xn? Very simple question to state. So let me present naive scheme 1. Okay, there are two naive schemes we present. Naive scheme 1. What does this scheme do? What does this scheme do? So what we do is compress and store each data point xi. So this part requires, so this compress is just using binary representation, so this requires n log cardinality of x bits. Okay. Right. There is no probability assumed on this. So this is the worst case analysis. This problem will only look for the worst case analysis. In fact, the probability version of many of these problems is still open. So we compress and store all the data points. So now when you search, to search for a y, we need to go over the entire list. Requires n computational steps. Okay, I can put order in, but n steps. Okay. So that's scheme 1. Memory wise, it is quite efficient, just requires n log x bits, just n words need to be stored, but computationally also it requires n step. This is the first scheme. Let's look at the second scheme. This is also another naive scheme, it's not too fancy. So what can we do? The goal we have in this scheme is to reduce this computational part. But what we will do is consider an array A of these many bits. Okay. Set A of I equal to, so A of I, you set it as 1 if, maybe I should use not A of I, let's say if A of x equals to 1 if x belongs to the list of observed tokens and 0 otherwise. Okay. So if you want to do it sequentially, as you get one token at a time, you keep on setting these bits to 1 and 0. And so now the search is very efficient. For search, check if A of y equals to 1. So this requires only one step. Search is very efficient, but the memory requirement is now n bits of memory. Sorry, requires not n, requires mod x bits of memory. So this is now mod x and this was just 1. So we are interested in the case where this mod x is large. The alphabet is very, very large. Okay. So in that case, this is memory wise. So there are a lot of possibilities of tokens which can enter. And in that case, maybe I should highlight this upfront. Sorry about this. So here itself we should say that is very large. The large number of tokens possible in comparison to the number of entries that you have. Okay, so this scheme 2 requires a large memory but is very efficient. It just requires 1. So there are these two schemes. One requires a roughly n bits. Forget about this log x. N log x bits, so roughly n bits, but also requires n steps computationally. The second scheme requires a large number of bits, mod x bits, but only one step computationally. And the goal is to come up with a scheme which requires roughly n log x bits, small number of bits, n log x bits, So this is n words. This you must store because you're observing n words. If you don't store this much, then there's no formal proof we have given yet, but later we'll give this formal proof. If you don't store this much, then there is no hope of recovering everything. Okay, this is something we haven't shown yet, but we'll show it later. And the other step, but the computational here requires n steps, and the other scheme requires a large memory, but computation only requires one step. Okay, so right, so this is your scheme, and now our goal is to come up with a great scheme, which, well, if wishes for horses combines these two bounds, so n bits memory and only order 1 computation. Okay, that's the goal. So that's the first part of this lecture, of this unit. Hash based scheme for compression of databases. Okay, so when we use the phrase hash here, we in practice you typically talk about deterministic hash, but as we have seen in the earlier classes, we are talking about a randomized hash here. Okay, not things like SHA-1, which are deterministic functions. Those are different kind of hashes. This theory uses randomized hash, or you can call it a keyed hash function, where a random key is used to select which function to use. So in the sense that the function can be randomized. Sometimes these are called keyed hash functions. So that's the kind of hash functions we'll use, and we recall this definition of a collision resistant hash family. Okay, or random hash function. Here what we said was that if you look at this function f, it's a random function. It starts from this universe and maps to, let's say, L bits, then probability that two different mappings, two different inputs get mapped to the same value is less than equal to 2 to the power minus L if x is not equal to x. Okay, that was one property we were looking after. And right, so we saw that randomly chosen function satisfies this property. Okay. However, we know that the construction of a randomly chosen function, if we want to use a randomly chosen function in a scheme, that will not yield an efficient construction because there are a lot of randomly chosen. There are a lot of functions, and we have to randomize over all of them, which will be very inefficient. So, for efficiency, what we would like to use is something which doesn't require that much randomness, and this is the notion of so-called a universal hash function, which I'll define next. So this property, let me call this property star, has a name, but here is a formal definition. We never gave it. And this is the definition of a universal hash family. More precisely, we are defining a two universal hash family, but since we don't look at more than two universal hash families, we can just call it universal hash family. What's the definition? So a family of mappings f from x to, instead of 0 1 l, maybe in this case it makes sense to just take it as m is a universal hash family in UHF. So it's a universal hash family if this property star holds. So f of x equals to f of x prime less than equal to 1 by m for all x not equal to x prime, where f is chosen uniformly over this family. So choose a random function of the family and this probability is over f, and this satisfies this. So we have already seen one example of such a family. F equals to set of all mappings f from x to m. Okay, this is a universal hash family, but this family is very large. So this is the set of all mappings. So this is a universal hash family. So what was it? We discussed its cardinality at some point in the class. So number of such mappings. So there are x cardinality of x points, and each of them can be given any of these values 1 to m. Okay, so you get m to the power cardinality of x. That's the number of mappings that you have. Huge, just exponential in x, and x itself is supposed to be very large. Okay, but the interesting point is that this property, if you just want to ensure this property, any functionality that can be satisfied just with this property can make do with more efficient constructions. And here is another example, which will be a much smaller family while giving similar guarantees. Okay, so this family, what we do is we think of x as a binary alphabet. We can always do that. Okay, so x is the k bit symbol, and just think of m equals to 2. So we just want a 1-bit hash. And this family f then is the family of all linear functions in finite fields. So this is the family of all functions fb, where b is a binary vector. Maybe I should call it v fv, where v is a binary vector of length k, and fv of x is given by summation I equal to 1 to k vi xi, and this summation is mod 2. Okay, so the final output would be 0 or 1. So namely, if this is so what do we do? This summation should declare this is AND. Here you multiply these two bits and then take their parity. If the total number of ones is even, then it's 0. If it's odd, it's 1. Okay, that's what mod 2 addition would do. So this is linear operation in this mod 2 field. So if those of you who know this language, this is linear operation over GF2, the Galois field of order 2. Okay, that's what it is. But very simple to see. Just take the AND of bits, just multiply these two bits, and then so you get k such bits. And if there are even number of ones in those k bits, then you take output to be 0, otherwise 1. Okay, that's what these mappings are. One for each v. And what is interesting is that the number of functions here is not m to the power x, which would have been 2 to the power k. It is just 2 to the power k, which is just the cardinality of x. Also, let's see if this satisfies the two universal hash property. So if for f which is uniformly distributed over this family, let's see what happens to the probability of collision. So probability that f of x equals to f of x prime, this probability is the same as, you can check this probability, that summation over I 1 to k bi of xi equals to summation I equal to 1 to k bi of xi prime mod 2. This equality is mod 2. Okay, where b1 to bk are random uniformly distributed bits. So I'm just calling them random bits. They show 0 and 1 with equal probability and they're independent. Okay, so now let's look at this guy. So bi xi minus this is equal if and only if summation I equal to 1 to k mod 2 is 0. So when is this thing 0? So you're given some xi equal to 1 to k, and since x is not equal to x prime, for x not equal to x prime, at least there'll be one bit which is not equal. So this can only be determined by looking at the support of this difference. Wherever you have, by the way, this minus and plus are the same. So in principle, this is just the XOR of these two bits. So wherever you have two different bits, wherever x and x prime differ, in those locations, we need to have even number of bi's that are 1. Okay, so look at the locations where x and x prime differ, and we need to have even number of ones in b at that location. Claim can happen with probability exactly equal to half. So why is it so? Why is this possible only with probability half? Okay. So suppose you have a sequence b1 to bk where this is equal to 0 mod 2. What I will do is I will just add I will just flip that location where xi is one of the locations where this thing is 1. I'll flip this bi to 0. Okay. So by flipping that bi to 0, I'll fix some one location and flip it to 0. This sequence, for any sequence where this is 0, I can find a sequence where this is 1 just by flipping one entry. So therefore, there are equal number of sequences where this is 1 and where this is 0. Okay, and therefore this can happen with probability half. And therefore, this probability that we were after is equal to half, which is 1 by m. So which implies this is f is a universal hash family. Okay, so this is an example of a universal hash family, and it's much smaller in size. But in fact, you may not be happy with this probability of hash collision. So you probably want a small probability of hash collision. And for that, what we can do is we can repeat this universal hash family multiple times. Okay. This is the third example. If we use R-fold product of the previous family, okay, this is the same as having f1 to fr independent random hash where each Fi is uniform on this F. Okay. Then, so to generate, so what's the family size then? It's 2 to the power, then this, I'll call this family, I'll denote this by R. Its size is 2 to the power Rk, and probability that Fx, this is the vector x, equals to Fx prime is equal to, because they are independent, and this is equal to 1 by 2 to the power R. Okay, so this is for large enough R, this is reasonably small probability, and you get the same R. Okay, so the point of these examples is to tell you that when you are thinking of a random hash, this random functions is not the only choice. There are more and more efficient constructions, and they are sort of algebraic constructions, and there are many variants of this constructions. We can do fancy constructions which are more randomness efficient as well. Okay, the trade-off is between this size of the family and the probability that you get here. And note that in all these constructions we got things with equality, but we only wanted things with inequality here, and that helps us. In fact, in many of these applications, this 1 can be relaxed to something like a delta. So that's like an approximately universal hash family, and that leads to further efficient constructions. Okay, so these constructions can be done. Okay, so we from here on we'll assume this universal hash family exists. So what do we want to do with this universal hash family? So here is our next scheme which uses a universal hash family. So this is a scheme. So we have already seen two schemes, both of them were sort of naive. So this third scheme is slightly, it's not too fancy, but slightly fancy. So what this scheme does is it maintains the same array. So it starts with let F be a universal hash family with range size m. Okay, so the output is m. And let F be uniform over this. So consider an array A of m bits. Okay. An array A actually of length m, where AL, so now AL is not a bit. AL is a linked list. You don't know what a linked list is. It's just some way of storing some sequence of data. What does it contain? Containing all xi's such that f of xi equals to j. Let's call it j. So that f of xi is equal to j. So what does it mean? So it means that what we do is we have this list here with m elements. So this is my A with 1, 2, 3, 4 m entries. And what happens in this jth entry is that you keep on adding all the tokens x, xj1, xj2, blah blah blah, and xj something, some total number n. Okay, such that so these are all stored in this location, and all of them satisfy f of xj. I equals to L j. Okay, sorry for my bad notation. So they all satisfy f of xi equals to j. We just put all these tokens here. So this kind of technique in database and in computer science, programming language, is sometimes called chaining. So we do this chaining and we put everything here. Okay. So now this is an interesting storage. Earlier we were putting all the elements, compressing and storing them. Now what we do is we don't put them all at the same place. We put them in m different buckets. So when a query comes for a query y, we go to the bucket a of f of y and look for y in all the elements stored there. So this is a randomized scheme. Okay, so if y was indeed present here, if y was already there, it will be definitely in the same bucket, and so when we go there, we'll find it. If y was not there, then you can still go there, and you will not find it when you compare with everything. That part is fine. The question is, so this will always work. With probability 1, you will find the right answer. If it exists, you'll find it, otherwise not. But what's the storage of the scheme? To store the scheme, you have to use so you have to store all these elements that came in. So you still have to store that memory required. N log x bits are needed to store all the data, plus, so this is still needed, you store all of it, plus m bits. I'll tell you what this extra m bits are. The memory requirement is n log x plus m bits, where we use one bit to indicate if a, I, or aj is empty or not. Otherwise, this is not fair. You'll have an empty symbol and it doesn't out. I mean, we will not be accounting for that part of the memory. So we assume that we use one bit to indicate if this array is empty or not. So there is some memory requirement to allocate these memory locations. Okay, so that's what this one bit to indicate empty or not is used. So total number of bits is this n log x plus n. Also, what is the computational complexity? So note that the worst case search complexity for this randomized algorithm is, this is a randomized algorithm. The complexity, the search complexity will depend on this function f. Depends on the longest chain that you have. That's the worst case complexity. Suppose you choose, suppose m is chosen, large enough so that with probability .99, say 0.999, there is only, or there is at most, one element in a bucket in a cell AJ. Okay. So in any cell AJ, there is at most one element. Suppose you can choose n. Then with probability 0.99, there the computational complexity of search, the computational complexity of search is order 1. Okay, because you just go there and there's just one element you search for. So what is this m which will ensure this? So we'll try to find this m. So claim m equal to 1000 and choose 2 satisfies this property. Okay, we'll call this property star. Satisfies star. So let's verify this. Proof. So what's the probability that you can find there exists I comma j such that xi is not equal to xj and f of xi equals to f of xj. So both of them went to the same bucket. Now, so this is over ij in 1 to n. What's the probability of this? This probability is less than equal to, we'll just take the union bound, I comma j such that xi is not equal to xj. Probability that f of xi equals to f of xj. Remember, we chose a 2 universal hash family. Therefore, each of these probabilities here less than equal to 2 to the power minus m. So this is equal to, this is less than equal to 1 by n. So this number here, this is just choosing 2 distinct elements out of them, and in the worst case, the maximum it can take is just n choose 2, because that will happen when all of them are different. So this is n choose 2 by m. And this probability is less than equal to 1 by 1000 if m is greater than 1000 and choose 2. Okay, so we'll choose that too. So we'll use this particular m. Therefore, so this completes the proof of the claim. Therefore, we have a scheme with order 1 computational complexity and 1000 and choose 2 plus n log x bit. By the way, this is approximately 1000 square, because this is n square plus bits memory requirement. Okay, so So we are almost there. This is almost like the best of two worlds. So we got this scheme 2's computational complexity, and we almost got scheme 1's memory complexity, except that you have n square here instead of n. Okay. So remember these two schemes that we saw in the beginning of this lecture. The two naive schemes. This one had this much memory, and the other one has much higher memory requirement, but only order one step search. And now the scheme using hash function that we came up with has n log x plus n square memory requirement. Okay. Question is, can we reduce the memory requirement to n? Okay. That's the question. Can we further reduce the memory requirement? And the answer is yes. Okay. So we can reduce this memory requirement. And that's our fourth scheme. So this is scheme 4. Now this scheme 4, it's very much like scheme 3, but instead of using a single hash table, it uses hierarchical hash table. Okay, it uses a hierarchical data structure. So it uses hierarchical hash tables. What it does is it makes m arrays a1 am, each array ai, aj, let's say, is that from, so it's of different size, is of size nj, say, and operates the same way as the array in scheme 3. Okay, so instead of having that one array, now we have multiple such arrays. Okay. So given a token xi, we store xi with f of xi equal to j. F is this UHF in array aj. How do we store this? Array aj has its own hash. Fj from x to nj. This is again the UHF associated with it. So pictorially, there are these multiple arrays, a1, a2, okay, so on and so forth, and where you store data entries, you go to that array corresponding to each xi, you go to some array, and then in that array you look for the hash for that array, and that tells you which cell to take this guy to, and that's where you add this guy. Okay, so you have a linked list there. So it's a two-level hash table. First hash table tells you which array to go to, and then the next hash table tells you where in that array should you store this guy. Okay, so it looks like we haven't changed much, but that's where the power of randomized algorithm will come in. So suppose maybe instead of ni I should, and it's fine. Sorry, this is a bad notation. I should have used a different name for this. I should call this, to be consistent with previous analysis, I should call this mj. Okay, the length of this guy should be called mj. Total is m, and these are mj. So these elements are m1, m2, m3, so on and so forth. And suppose there are nj elements assigned to the array aj. So this hash, actually we should not think of this hash as from x to nj. This hash is from, we only need to worry about these elements here. So this will take these elements, these nj elements assigned here. This is some pre-stored thing that we can, that can be stored, and it will be assigning those nj elements. These are not 1 to nj, but to some nj elements, but we can use the same, the mapping from 1 to nj we can use. That mapping is some fixed mapping that we are storing here. So we are not accounting for that. Okay, and we can map it to mj elements. So suppose you have these many elements assigned to each. Then if we use j equal to 1000 nj choose 2, the probability of having more than one element in any cell of aj is less than equal to 1 by 1. However, we don't know which cell we want to ensure this for, but that's the sort of the hidden part of this question. We only want to ensure this for a single cell. So we only want to ensure this for the array aj where j equals to f of y. Okay, so this it's not that we wanted to hold for all j at the same time. We only wanted to hold for one j, and therefore this probability suffices. Right. So you can do this. Now, if you set this mj, then with probability 0.99, thus for mj equal to 1000 nj choose 2, if you set this mj, um, the search complexity is order 1, because the cell containing Y will only have one element. The expected number of bits stored is equal to, so we must store all the tokens, so that's this, plus now, and that's the second part, expected value of summation L equal to 1 to M 1000 J equal to 1 to N 1000 Nj choose to, and the random variable here is Nj, the number of elements in the bucket. So this can be written as this, nothing to, so we'll just analyze this last part here. This part is constant. This expected value summation J equal to 1 to N Nj choose to equals to is less than equal to expected value summation J equal to 1 to M, and this is just Nj square, but Nj itself is summation I equal to 1 to N indicator function f of xi equals to j. That's what Nj is, and this guy is just less than equal to Nj square. So we can expand the square. This kind of trick, I'm not sure if you've done this before, but this is a very handy trick. Very simple but handy trick is to expand this square. So this is a very complicated looking term, but we can express this square as I comma I prime both between 1 and n, indicate a function fxi equals to j, and multiplied with indicator function fx I prime equal to j. And now what we can do is we can take this summation outside because of linearity of expectation. Expected value j equal to 1 to m. And this product of two indicator function can be written as fxi equals to fxi prime, you can check this, equal to j. This is 1 if both of them are 1, and this is 0 if either one of them, if this condition is disqualified, if this condition doesn't hold. Okay. Now, what is this event here? This is the same as saying that these 2 points coincide. So this is summation I comma I prime expected value of the indicator function we were asking it to be j, but j can be anything, so this can happen if these two are equal. This sum is exactly equal to this indicator function. So when you take expectation, this becomes summation over I prime probability f of xi equals to f of xi. So the worst case thing will occur when all the elements are distinct. Okay. And so this worst case probability is less than equal to either they are same, in which case this will be true. Okay, if they are same, this is true. So that's I equal to I prime. In that case, this must be true. That probability is n, that's first term, plus now I can be any number here, and I prime is different from I, and we are looking for this probability. which is less than equal to 1 by m if x1 to xn are distinct, which is the worst case situation. Otherwise, we can only do better. So this is the worst case situation. But in the worst case, this is less than 1 by m. So this is less than equal to n plus n into m minus 1 by n. Okay. In particular, for m greater than equal to, let's say for m equal to n, the expected number of bits stored is less than equal to 2n plus n log x. Okay. So finally, this is a scheme that we were looking for. It only requires these many bits of memory and has order 1 computational complexity and requires these many bits of memory. Okay. So this scheme 4 attains memory requirement or memory complexity of scheme 1 and computational complexity of scheme 2. So this is, in this sense, the best of the both worlds scheme. Okay. Now, so for search complexity of 1, we have brought down the memory complexity to order n. And the question is, can we improve further? Is there any hope of improving further? Note that this is in expected sense. It's not in the worst case. But we can make this expected sense a probabilistic thing. Right? We can say this holds with large probability by using Markov's inequality. There will have to be an extra factor of, let's say, 1000 if you want to make it hold with probability 1 by 1000. So then the probability 1 by 1000, this expected value, the number of bits stored is less than this, times 1000. Okay. So the question is, can it be improved further? This average length of a randomized scheme, can it be improved further? And in the next lecture, we will see, we'll show a lower bound showing no, this average length cannot be improved further. Okay. That lower bound is also very interesting. This is a little bit, this lecture is slightly off topic from the regular information theory course, but I feel that hash is a very important compression scheme, and random hashes are used both in information theory and computer science quite a bit. So it's an important topic to cover. Also, the lower bound, the optimality bound that we'll see in the next class, is very information theoretic.